thanking the organisers for putting on such a great workshop. My name is Ben. I'm from the University of Bristol in the UK. I'm the second Ben giving a talk at this workshop from Bristol, but we're not all called Ben. This is some recent work I've done with my two supervisors here. So let's get into it. So yeah, in this work, we're going to consider kind of quite a general paradigm of quantum computation, in which you have some free operations acting on resourceful states. Specifically, we're going to give some no-go results on the possibility of implementing the Hadamard gate under the conditions of kind of these free operations, and specifically some kind of arbitrarily resourceful ancilla. And more conceptually, we're kind of going to touch on this point throughout the talk, but we're going to give evidence that whilst for the resources of magic and entanglement, you can basically siphon off the resource to some supplementary state. But for the resource of coherence, this is impossible. So kind of coherence is special in this context. And technically, kind of the technical results that we show basically relate to the resource theory of coherence. So there's some results there that maybe stand independently. Great. I'll start by kind of motivating some of the questions that led us to this work. So let's kind of start by talking about the Clifford plus T gate set, which is maybe the most widely studied gate set in quantum computing. I'll flash up the symbols and the matrices of these gates in case you're a bit rusty. And we know that Cliffords by themselves, so that's these first three gates, the Hadamard controlled knot and phase, are classically simulable by this Gottesman-Keneal theorem. And we call anything not Clifford magic. So specifically this T gate at the end would be called a magic gate. We have if you square the T gate, you get the phase gate, but we kind of include both because it turns out the T gate is a lot harder to implement in general. And already here, there's kind of something conceptual, I think, which fits with the theme of this conference, which is that the Hadamard, the C naught, and the T, you can kind of conceptually think as respectively providing these kind of three big resources of coherence, entanglement, and magic. So if you don't have one of these gates, then you're kind of lacking in one of these quantum resources, and you won't be able to do universal computation. Let's zoom in on magic for a second. So basically, all the leading approaches to performing error correction allow you to do Clifford gates in an easy fashion, but the magic gates are kind of more difficult. And this leads to this kind of approach to quantum computation in which you, instead of applying a T gate, you can apply these adaptive Clifford operations and some T state. So here, this is the T acting on the plus state is called the T state. And overall, this circuit allows you to implement the T gate. So here, your operations are just adaptive Clifford operations, but you're using this resourceful magic T state in order to implement the T gate. And yeah, so for every time we have a T gate in our circuit, we can replace it with this little circuit, which is called a gadget. And so conceptually, this is a model in which you have free operations, which would be Cliffords in this case, acting on some resourceful state, which would be some copies of this T state. I'm going to return to this diagram a few times. This is kind of representing the universal gate set of Clifford plus T. And in this case, we can basically cut out the ability to perform the T gate and replace it with this T state. And then using the remaining operations adaptively, we can still achieve universality. So a natural next question that you might ask is, what about the other gates in Clifford plus T? Can you kind of cut these out and still have universality? So C naught would be the natural next one to think about. And my claim is this kind of naturally puts you in the measurement-based quantum computing framework. So if you remove C naught from this gate set, then the only gates that remain are basically single qubit gates. And yeah, measurement-based quantum computing, in a general sense, involves performing these adaptive local measurements on some entangled resourceful state. And the way we're going to incorporate this into our framework is that if I give you the ability to perform Z measurements and also apply Hadamard S and T, then this implies the ability to measure in certain bases, which are universal. So in practice, measurement-based quantum computing is about doing measurements, but given the ability to perform these unitaries and do computational basis measurements, then this implies the ability to basically have a universal model of quantum computation. And there's also kind of a more succinct model in which you can do this just using Z and X measurements. But now your resource state is a hypergraph state. So you can kind of think of this as just if I give you the ability to do the Hadamard and computational basis measurements, then there exists this resourceful state such that universality is possible. So here in this case, back to this little diagram, we kind of have a similar paradigm in which you can now cut off the C0 as like the entangling gate and replace it with this state and still have a universal model. So this is basically how we started the project, was thinking, well, you have this universal gate set, you can cut off the T gate in kind of the magic case, and this leads to a model in which all the resource of magic is in a state. You could cut off C0, and then you have a model in which all of your entanglement has kind of been siphoned off to some state. And the remaining kind of question to us was, well, what about the Hadamard gate? There's also the case of cutting out the phase gate, but as I mentioned, T squared equals phase, so this case is kind of redundant. So really this, for us, was kind of a natural remaining question in this picture. And we're basically going to provide no-go results in this case to say that it's not possible. So yeah, just to summarize our motivation. So can we find kind of a unified framework that kind of incorporates some of these cases? Concretely, is there an implementation of the Hadamard gate using only C0, S, and T gates, classical control and computational basis measurements, and some arbitrarily resourceful state? And more generally, I've kind of already touched on this a few times, but where can we put the cut between operations and states and still achieve universality? So we've seen that for the resources of magic and entanglement, there are quite natural models. But what can be said about coherence? Great. I'll move on to kind of talk about some of our results. So the first idea you might have is, well, we saw this magic state injection gadget, and you might just ask, well, does there exist kind of a corresponding gadget for the Hadamard? So here, like W and V might be some product of C0, S and T gates. And right off the bat, we can actually simplify this kind of circuit already. The first thing is we can replace this classical control with quantum control using this thing called the principle of deferred measurement. So although quantum control is a lot harder to do experimentally than classical control, mathematically, if this top circuit exists, and then this kind of second circuit also exists and is equivalent to the top one. And if we want to be able to implement this deterministically, then it must be independent of the outcomes of the measurement. And so actually we can just think of having a partial trace at the end. So really we're just considering this kind of quite simple type circuit and asking if there's a product of possibly quantum controlled gates of C0, T, and S for U. Just some kind of quick definitions. So these gates are all instances of what's called incoherent unitaries, which essentially just map computational basis states to computational basis states, possibly multiplied by some phase. And yeah, lots of the gates we know, like C0, ST, Toffoli swap, or the Pauli gates are all incoherent in this sense. But for example, Hadamard and the quantum Fourier transform are coherent gates. And we're kind of going to be slightly more general and ask just, does there exist some, again, possibly quantum controlled, but just some incoherent U and some arbitrary state such that this equation at the bottom is true, which I'm just pulling from this circuit at the top. Again, a couple more preliminaries before we get on to the first result. So we're going to use this definition of generalized control unitaries, which essentially is just, you might want to apply a unitary based on the combination of some multiple outcomes of measurements. So this is kind of the generalized version of a quantum controlled unitary. There's a quick lemma you can show, which is that if you do quantum control of incoherent unitaries, then you still end up with something incoherent. And I'll mention now, this is potentially the crux of why our no-go result is that in the resource theory of coherence, you have the quantum control keeps the free set free, but this is not true for entanglement and magic. So already you could kind of zoom in on this as potentially the reason why things don't work. Incoherent states are just diagonal in some preferred basis. And we're going to see this map called the dephasing map, which just sets the off-diagonal terms to 0 in some particular basis. Great, so yeah, our first kind of observation was that if I give you kind of some free operations of this form, so I allow you to prepare and measure computational basis states, do some adaptivity, and apply some set of unitaries, and I give you some resourceful state gamma, then the channel I basically wrote earlier is the most general channel that you can implement. But here, this unitary U really corresponds to this set of quantum-controlled unitaries. And we claim in the paper that this kind of covers quite a lot of models of quantum computation. But specifically in our case, as I said, we're going to have U being incoherent unitaries. So this controlled set is also incoherent, and swap is incoherent as well. So we can basically take this partial trace over the second system without loss of generality. Great, on to our first result. So this is the question we're asking in this case, kind of, does there exist an incoherent U and some state gamma such that the overall channel is equal to the Hadamard? And there's this interesting work in which they basically claimed that this was possible for a certain form of channels, and I was a little bit confused. And then I saw they released an erratum after the work, in which they had a small example, which we've then generalized as part of our first result. So formally, the result is if you have a channel that has this property with the dephasing map, then for any input state, the overall kind of induced channel cannot implement any coherent unitary. So in this work, they had a small counterexample for a qubit, and we basically formalized that argument and generalized it to arbitrary dimensions. But really, we're kind of extending the argument that was in this erratum. And we can show that the channel I've written at the top satisfies the form of this lemma. And so bringing it together, what we have is that if I operationally give you the ability to do these things that I've been mentioning, then even if I give you some arbitrary ancilla, you're not going to be able to implement the Hadamard gate. So this is kind of how we get our first result. The second result is we basically wanted to do something slightly more approximate to show that this isn't completely not robust. And so we have a similar kind of form here, where if a channel, in this case, commutes with the dephasing map, then we're able to show lower bounds between the induced channel, so using some arbitrary ancilla, and n Hadamards in the induced trace distance. And again, to kind of interpret this means if I give you the ability to perform these things, the resulting channel will satisfy the condition of this lemma. And in the case of a single Hadamard, we get this lower bound of a quarter. So I'm not claiming this bound is optimal or particularly good, but we just wanted to find something to show that you couldn't get arbitrarily close in induced trace distance as like a first bound. Great. There was one other direction in which we wanted to make our result robust, which is you might think, if I give you the ability to do a single Hadamard, then maybe you could use this to unlock all of the resource in a state, and then you could do 2 Hadamards or multiple Hadamards, which would be quite strange. So for example, specifically, you might be worried about circuits of this form, in which, let's say I give you the ability to do some incoherent unitary U, and then a single Hadamard, and then some incoherent unitaries again. Maybe from this, you could use the resourceful state gamma to implement 2 Hadamards. And we're also going to basically rule out this case. So again, from the arguments I've kind of said previously, we can instead replace the classical control with quantum control and take a partial trace at the end. And ultimately, we'd end up with an equation at the bottom of this screen. We can see that the ancilla must be left in a pure state at the end, but a priori, it could kind of depend on the input state psi. However, you can maybe already see quite quickly that this would kind of violate a form of no cloning, because the quantum information of the state psi, so the input psi, is kind of all preserved in the first 2 registers. And so for this ancillary state gamma to have any information about psi would kind of violate a form of no cloning. So that's just a hand-wavy argument as to why we can basically conclude that our ancillary state must be left in a state that's independent of the input psi. So this is kind of step 1 of our argument. And now we're basically going to bound the resource content of this gamma and gamma prime. And specifically, we're going to use a resource quantifier called the coherence rank. So let me introduce that. So the coherence rank is basically just the number of terms you need to write your state as a linear combination of computational basis states. So for a specific computational basis state, the coherence rank is 1. If you have the superposition of all bit strings, then you'd have a coherence rank of 2 to the n. And also we have this nice property that it's multiplicative on tensor products. So what we're going to do is we're going to input kind of the two extreme cases of 0, 0, and plus, plus, and we're going to get a contradiction in terms of the coherence rank of this ancillary state. Again, this is the equation that we have landed on. And this is me just subbing in psi equals 0, 0 and psi equals plus, plus. Again, there's like a very quick lemma, which is fairly intuitive, which is basically this unitary on the left-hand side. This is just 2 incoherent unitaries v and u, and then sandwiched with a Hadamard. And this can at most double the coherence rank, and in the worst case, halve the coherence rank, which is maybe quite intuitive. Like a Hadamard can just kind of double the number of terms in superposition, or halve them in the worst case. So let's let R and R prime be the respective coherence ranks of the ancillary state at the beginning and the end of the computation. Then these equations imply, so the top equation, on the right-hand side, we have the coherence rank of this state is going to be 4R prime. And on the left-hand side, we're going to start with something of coherence rank R. And then at most, this could double to 2R, or it could go to R over 2. So we end up with this equation of basically bounding the coherence rank. And we can do the same thing with the second equation, where on the right-hand side now, our coherence rank is just R prime. We start with 4R on the left-hand side, which could then go to 2R, 8R after applying that unitary. And this implies that 4R prime is in the interval 8R, 32R, which is a contradiction with what we have above. So this is kind of a sketch of our argument to say why overall this type of circuit in which you have like a single Hadamard and you're attempting to implement 2 Hadamards using a resourceful state is not possible. So that was just a sketch, is kind of the formal statement. So if you have some circuit which is basically using K Hadamards, then you can't really use this ancillary state gamma to implement strictly greater than K Hadamards. And again, we can kind of summarize this in our context with this theorem. So this is our third result. Great, I'll just kind of summarize and then conclude with some future directions. So we've shown that basically in this picture, you cannot replace the Hadamard gate with a resourceful state, specifically in Clifford plus T. And we've kind of argued that you must have some coherence in your operations to do universal quantum computation. And my claim is that this really contrasts with these other resources of magic and entanglement. And so this is kind of something special about coherence. And yeah, our proofs kind of dipped into the resource theory of coherence, but the details are all in the paper. I think there's lots of kind of interesting future things to go and look at. A natural one is just completing our analysis and improving our bounds. Or specifically, we didn't find any bounds for kind of using K Hadamards to implement N Hadamards. So that's kind of a natural open question. I think there is natural things with measurement-based quantum computing to try and incorporate here. So we kind of focused, although we incorporated it into our general framework, we really focused on this idea of universality in the circuit model, which you could think of as maybe implementing any unitary. Whereas arguably in the measurement-based setting, the concept of universality is maybe more to do with preparing a given state. And this means you really have to think about the dimension of the ancilla, because otherwise you could kind of just encode all states into some resourceful ancilla, and then just by tracing out, you could prepare any state. My point is just there's a bit more subtlety in this case. I think there's potentially some interesting connection between coherence and measurement incompatibility. I touched on like ability to perform the Hadamard kind of gives you this ability to measure in the X and Z bases. And so a more general statement of our results could be that perhaps you either need some coherence in your operations or you need some incompatible measurements, and somehow computationally these are connected. Finally, just a few points on general resource theories fitting with the theme of the conference. So yeah, I think there's an interesting point about classical control and quantum control in our work here. I mentioned that I think a lot of the reason why this worked is because if you take quantum control of free unitaries in coherence, then this still gives you something free. And this is not true for the resource theories of magic or entanglement. So there's a question about, are there other resource theories for which you can take the quantum control of the free set and still remain free? Or is coherence kind of the unique resource theory? I think that's quite an interesting question. I also see, like in hindsight, that there's maybe this trade-off underpinning our results between unitarity and resource generating power. So we had channels of this form, and you could maybe argue that in order for this to basically boost the resource content of the unitary U using the state gamma, maybe the only thing you could actually do is kind of swap in this state. But then if you were to swap in this resourceful state, this would compromise on the overall channel being unitary. So perhaps there's actually a more fundamental result. And this trade-off was kind of underneath the hood the whole time. In general, I also think there's an interesting question of boosting the resource content of channels kind of using resourceful states, and when that's possible in a given resource theory. And finally, I've touched on this a few times in the talk, but I think conceptually it's interesting to think, if you want to do quantum computation, what's kind of the minimum operations that you need to be able to do? And which of the resources can you kind of just siphon off into some resourceful state? So what kind of do you need to be able to do in your operations? I think is quite a general, interesting question, which you could ask for lots of resource theories. So yeah, thanks so much for listening, and I'm happy to field any questions. Thanks.
Yeah, thanks. Questions? Oh. Yeah, quite a lot of questions.
Thank you. There are many, I think there have been many studies to implement non-covariant unitary operation by a covariant operation with some auxiliary system. A famous example is the catalytic coherence paper by the Hadamard. And there are many, I think, many other results. So what's the relation with such previous results and your result? Of course, the setup is slightly different because their subject is general unitary, not restricted to Hadamard gate. But is your result stronger than previous one, or?
Remind me, covariant operations are ones that commute with the dephasing map. Is that right, or what? Could you remind me that definition?
Generally, in the paper, only using the energy conserving Hamiltonian or covariant operation, and state is have many coherence, and they want to implement some non-energy conserving unitary by using. So the Hadamard gate can be implemented by the Hadamard protocol.
Okay, thank you for the question. I'm not super sure, aware of this work specifically. I think the channels we're considering didn't seem to neatly fit within the resource of coherence, because we're really allowing this arbitrary resourceful state kind of meant our channels could be arbitrarily resourceful, but the condition was really forcing them to be unitary. So that's maybe a short answer, but I'd have to go and look specifically at the works you're talking about to see how it fits.
Okay, thank you.
Thanks.
Yeah, okay.
So thank you for your very insightful talk. So I think in the proof of the impossibility of the implementation of multiple Hadamard gates based on the single Hadamard gate, you use the self inverse property of the Hadamard gate. But do you think this work is also applicable to any other coherent gate, just other than Hadamard gates? I don't know what kind of other coherent gates exist, but.
Thank you, that's a great question. Yeah, so we specifically focused on the Hadamard for this third result. But I think this would hold in general, because really the argument that we kind of formalized in the paper was really to do with bounding the coherence rank. So if you have any unitary that is capable of generating coherence like the Hadamard, this would also be able to change the coherence rank, and you would come up with a similar argument to here in terms of a contradiction of you would input a very coherent state like the plus states here and the zero states, and I believe you would come up with a similar contradiction, but we really focused on the Hadamard in this context.
Thank you.
Thank you.
There was a question over there.
Right. I'm curious, in the case of magic, the stabilizer formalism is extremely powerful because you can say, you know what, magic is what allows you to send powers to some things that are not just powers. I'm curious if in this picture, the stabilizer formalism can also tell you something interesting, as in, you know, the Hadamardness of a state or a transformation is something that can send z's to x's or something like that. Is there a picture like that you can draw?
That's interesting. You mean like, is there some kind of tableau formalism for coherence? Could I think about your question that? That's a great question. I don't know the answer. Like another kind of future thing that we didn't really look at was the question of, I guess, simulating incoherent operations. And we've heard some talks this week about, you know, if you have magic states, then you can kind of quantify the runtime of your simulation in terms of the number of states. And I kind of see what we've done as maybe a no-go result towards showing that really there's a big distinction and you can't really do this for coherence. But I think there's a lot of work to be done. And you're right, maybe there's some kind of special property of Hadamards and coherent gates in general, which is like a normalizer of some subgroup, like in the case of magic, but I really haven't looked in this direction. Thank you.
There is a question of Ruichi.
Yes. Thanks for the talk. So the state gamma there, do you have any restriction on the dimension? Like, are you considering the infinite dimension as well there?
In our proofs, we didn't put a restriction on the dimension, but we did say it was finite dimensional. I think my intuition is I think the proofs would go through in the infinite dimensional case, but we allowed it to be unbounded, but it was finite dimensional.
I see, because I was checking, because if this is for the finite dimension, and if I'm not mistaken, then say a curiosity Tajima and I, and also independently, the Yushan Yan and Julio and Renato Lena showed the no-go theorem part as sort of like a special case of the general theory. Not really restricting the Hadamard gate implementation, but like any coherent generating unitary cannot be implemented exactly in that form. And that is a trade-off between how much coherence you can generate by the target unitary, and for us, the dimension of the answer system, and for them, the amount of coherence. So I'm just interested in like how we could sort of understand each other. Yes.
Sure. So in these works, was the ancillary dimension left completely? It could be infinite.
Yeah. So like if you want to exactly implement it, you need infinite dimension. Basically, the dimension diverges as the error goes to 0. So that in principle, that doesn't prevent you from getting the infinite dimensional answer system, and we're still working on an infinite dimensional case and trying to see if we can extend the proof and so forth. But it would be nice to discuss more.
That'd be great to talk about. Yeah. Yes. I don't know what happens.
All right.
Thank you so much.
Yeah. Okay. Thanks for the talk.
Thank you.
And we're